First, where did the Frisbee come from? Well, it began in the late 1800s with the Frisbee Baking Company of Bridgeport, Connecticut, who made pies that were sold to many New England colleges. Hungry college students soon discovered that the empty pie tins could be tossed and caught, providing endless hours of game and fun. In 1948, a Los Angeles building inspector named Walter Frederick Morrison and his partner Warren Franscioni invented a plastic version of the Frisbee that could fly further and with better accuracy than a tin pie plate. This eventually is what made our common day Frisbee. On to the physics in Frisbee. Two factors influence the flight of a Frisbee: gravity and air. Gravity acts on all objects the same way, accelerating their mass towards the center of the Earth at 9.8 meters per second squared. These factors end up affecting the Frisbee's lift and drag, which are key forces that act on a Frisbee during flight. Lift is the force that allows the Frisbee to stay airborne, and in flight it opposes the force of gravity on the disk's mass. The Frisbee itself creates this lift force as it flies through the air. Because of the Frisbee's curved shape, the airflow above it must travel at a higher velocity than that underneath, thereby creating low pressure above and high pressure below the disk. Under the Bernoulli principle, the difference in pressure causes the Frisbee to rise or lift. Drag is the resistant force on the Frisbee, perpendicular to the lift, and it acts against the disk's movement through the air. The angle at which the Frisbee is thrown, aka the angle of attack, affects both lift and drag. To fly well, the Frisbee needs enough lift and not too much drag. We tested these launch angles to find out which of these angles provided the Frisbee with a higher overall distance. First, the negative angle, 0 degrees, and a positive angle. When the Frisbee is thrown tilted downward, it does not have much lift and so it quickly falls to the ground. When the Frisbee is thrown relatively horizontal, it has a good amount of lift and consequently flies relatively far, at least much farther than when the Frisbee was thrown tilted down. When an even larger launch angle is used, the Frisbee has more lift. You may have noticed, however, that although the Frisbee thrown upward flew relatively high, it stalled out rather abruptly near the end of its flight, causing it to not get a lot of distance. Of the three launch angles tested, the horizontal launches resulted in the overall best Frisbee throws in terms of overall distance. This diagram shows the forces on a Frisbee in flight. The arrow V shows the direction of flight, V stands for velocity. The downward arrow mg is the weight of the Frisbee. The backward arrow D is the force of drag. The upward arrow L is the force of lift. Both lift and drag change as a function of the angle of attack, which is A, and is shown here as the difference between the direction of flight V and the direction the Frisbee is pointing, D1. Here's a better visual representation of how lift and drag work. Look at the way the wind forms through the bottom and the top of the Frisbee. Here's it at 0 degrees. Here you could see it at a positive angle. And here you can see the Frisbee at a negative angle and how the wind forms around it. Next, we wanted to see on how throwing against wind and along wind will affect the Frisbee's overall range. First, we threw the Frisbee against the wind. Next, we threw it along the wind. This diagram shows basically what happened. Throwing against the wind added more of a force compared to throwing with the wind. Therefore, that's why the Frisbee going with the wind flew further than against the wind. This basically sums up the physics behind a Frisbee, and I hope you understand how you could do things like this. Or this. And if you're good, maybe this.